6.1 Energy and the Conservation of Energy. Without energy, nothing could ever change. Pure energy itself can not be smelled, tasted, touched, or even heard. However, energy does appear in many forms, such as motion and heat. Energy can travel in different ways, such as light and sound waves, and in electricity. The workings of the entire universe, including all of our technology, depend on how energy flowing and changing back and forth from one form to another. What is energy? Energy is a quantity that measures the ability to change. Anything with energy can change itself or cause change in other objects or systems. Energy can cause changes in temperature, speed and position, momentum, pressure, or other physical variables. Energy can also cause change in materials such as burning wood, changing into ashes and smoke. Energy measures the ability to change in a physical system. Examples: a gust of wind has energy because it can move objects in its path. A piece of wood in a fireplace has energy because it can produce heat and light. You have energy because you can change the motion of your body. Batteries have energy. They can be used in a radio to make sound. Gasoline has energy and can be burned in an engine to move a car. A ball at the top of a hill has energy because it can roll down the hill and move objects in its path. The unit of measurement for energy is the joule, J. 1 joule is the energy needed to push with a force of 1 Newton over a distance of 1 meter. The joule is an abbreviation for 1 Newton multiplied by 1 meter. If you push on your calculator with a force of 1 Newton while it moves a distance of 1 meter across the table, 1 joule of your energy is converted into the energy of the calculator's motion. And variables. The universe is huge and complex. The only way to make sense of it is to think about only a small part at a time. If you want to understand a car rolling down a ramp, you don't need to concern yourself with the sun or the Milky Way galaxy or even the room next door. When you want to understand something, you focus your attention on a small group called a system. A system is a group of objects, effects, and variables that are related. You set up the system to include the things you wish to investigate and exclude the things that don't matter. When you are trying to find out how a system works, you look for relationships between the important variables of the system. For example, imagine you are doing an experiment with a car rolling down a ramp. The car and the ramp are the system. The car's speed is one important variable. Time, position, mass, and the angle of the ramp are other variables. The ideal choice of a system includes all the objects, effects, and variables that affect what you are trying to understand. Figure 6.1. To understand the motion of a car on a ramp, you might include the car, the ramp, the mass, and speed. The fewer the variables, the easier it is to find important relationships. You can include more variables, like friction from wheels, after you understand how the more important variables fit together. Conservation of energy. Energy appears in many forms, such as heat, motion, height, pressure, electricity, and chemical bonds between atoms. Systems change as energy flows from one part of the system to another. Parts of the system may speed up, slow down, get warmer or colder, or change in other measurable ways. For each change transfers energy or transforms energy from one form to another. Friction transforms energy of motion to energy of heat. A bow and arrow transforms energy in a stretched bow into energy of motion of an arrow. Figure 6.3. Energy can never be created or destroyed, just converted from one form into another. The idea that energy converts from one form into another without a change in the total amount is called the law of conservation of energy. The law of conservation of energy is one of the most important laws in physics. It applies to all forms of energy. The law of conservation of energy tells us energy cannot be created from nothing. If energy increases somewhere, it must decrease somewhere else. The key to understanding how systems change is to trace the flow of energy. Once we know how energy flows and transforms, we have a good understanding of how a system works. When we use energy to drive a car, that energy comes from chemical energy stored in gasoline. As we use the energy, the amount left in the form of gasoline decreases. And energy transformation. You may do an experiment in class that follows a rolling marble up and down a hilly track. The marble starts slow, then speeds up as it rolls down the first hill. The marble slows down almost to a stop as it rolls up and over the second hill. The marble speeds up again as it rolls down the second hill. How do we explain the changes in the speed of the marble? The easiest way is to think about energy. The marble and the track are a system. This system has two major kinds of energy called potential energy and kinetic energy. Potential energy is due to position. When you lift the marble off the ground, it gets potential energy because of its height. The higher you lift it, the more potential energy it has. Kinetic energy is energy of motion. The faster the marble moves, the more kinetic energy it has. The marble has zero kinetic energy at the start because it is not moving. The marble has the most kinetic energy when its speed is greatest. Assume the system starts with the marble at the top of the first hill, figure 6.4. Conservation of energy says the total energy stays the same as the marble moves up and down. As the marble moves down, it loses potential energy. Where does the energy go? It changes into kinetic energy, which is why the marble speeds up. To get up the hill, the marble needs potential energy. It can only get it by reducing its kinetic energy. That is why the marble slows down as it goes up the hill. Its kinetic energy is being changed into potential energy. The potential energy changes back into kinetic energy again as the marble rolls down the hill. In your life. A joule is a tiny amount of energy compared to what you use every day. 1 joule is just enough energy to lift a pint of ice cream 21 centimeters off the table. The same pint of ice cream releases 3 million times as much energy when it is digested by your body. Some units of energy that are more appropriate for everyday use are the kilowatt hour, food calorie, and the British thermal unit, figure 6.5. The table below gives some average values for the energy used by humans in daily activities. Conserving energy in the everyday sense. Almost everyone has heard that it's good to conserve energy and not waste it. This is good advice because energy from gasoline or electricity costs money and uses resources. But what does it mean to use energy in the everyday sense? If energy can never be created or destroyed, how can it be used up? Why do smart people worry about running out of energy? When you use energy by turning on a light, you are really converting energy from one form, electricity, to other forms, light and heat. What gets used up is the amount of energy in the form of electricity. Electricity is a valuable form of energy because it is easy to move over long distances through wires. In the physics sense, the energy is not used up but converted into other forms. The total amount of energy stays the same. Electric power plants don't make electrical energy. Energy cannot be created. What power plants do is to convert other forms of energy, chemical, solar, nuclear, into electrical energy. When someone asks you to turn out the lights to conserve energy, they're asking you to use less electrical energy. If people used less electrical energy, power plants would burn less oil, gas, or other fuels in producing the electrical energy as well. Many people are concerned about running out of energy. What they worry about is running out of certain forms of energy that are easy to use, such as oil and gas. At the beginning of the industrial age, the planet Earth had a certain amount of oil and gas. It took millions of years to accumulate, and once it is used up, there will be no more. When you use gas in a car, the chemical energy in the gasoline mostly becomes heat energy. It is impractical to put the energy back into the form of gasoline, so we say the energy has been used up even though the energy itself is still there, only in a different form. Other forms of energy, such as flowing water, wind, and solar energy, are not as limited. Many scientists hope our society will make a transition to these forms of energy over the next 100 years. Here and answer these questions.